Part 2 of water, unit 1. And you're all wishing you were at the beach right now, right? I don't know. But I do. Snorkeling, of course, or fishing. I like to fish. Not as much as I used to because fish populations are declining. So I want to try to protect the fish as much as possible. So putting a hook in their mouth just for fun. Good survival skill, but probably not the best. You wouldn't hook a bird in the mouth, right? You wouldn't hook a squirrel or a rabbit in the mouth. And then that's just not good for their survival, right? Okay. So this question is not in your notes. It is a discussion question. It's kind of your bell work today. And it says, is this water fresh or salt? Because you really can't tell, can you? Okay? How would you be able to tell if this water was fresh or salt? What would you need to do to be sure it was, okay? And it says refer to yesterday's notes, but part 1 is what I meant. And so just take, 10 seconds to think about what you would have to do scientifically. Tasting it, I know that's the first thing you guys thought. And if you were, there are some lakes that you could stand on the beach. Like if you woke up on the beach on a lake, you would not, and you couldn't see the other side, you might think you were on the ocean somewhere. So what would you have to do? Okay. Could you test the density, okay, of it? That's probably the easiest way to do it. So, other than tasting it, and there are some other things you can do, which we're going to learn about today in this class later. So, we're on slide, 17. There it is, slide 17. And you have to be able to, in this class, explain the effect of water temperature on the solubility of salts. It's really kind of simple because you all like candy. All right, now wait a minute, Mr. Keene, what are you doing? You tell me I can understand this concept because I like candy. Okay. Yeah, it's true. How do they make hard candy? Even cough drops and butterscotches and mints, little peppermints you get at restaurants. And one of the coolest things is those sticks that have the crystalline flavored sugar on the end, those lollipops that look like rock candy, okay? Because you like candy, okay, most people do. That's how you should know this concept. And as the temperature increases, and that's what all of these charts, all these graphs are showing, the solubility of salts increases. So, and other dissolved substances, solid substances, okay? Solid is the key word here. Salts are solids. So if I boil water, I can add more solute in it. Okay, and that's where the candy part comes in. Because you can super saturate a liquid by heating it up, and then you add more and more substance to it. And then when you in the candy case, sugar, if you let that sit over time, it will adhere to and recrystallize on a stick, which is where you get your rock candy lollipops from. So anyway, simply put, the higher the temperature, the greater the solubility of most solids. And that's what you have to just be concerned with, okay? Even though there's some errant ones, like this purple one here, okay? And even though sodium chloride is only mildly affected by the increase, okay? virtually all are proportional to temperature, okay? Solubility. So what does salinity mean? We talked about salinity in the last set of notes as well, but we really didn't define it very well. Salinity, it has the term sal, which is salt. It's Latin, okay, for salt. And it's the oldest known flavor additive, to foods, salt. Salt was at one time traded as money, as currency, and in its importance in human life. Okay, so that's where the term salinity comes from: is how much salt or other dissolved salts and solids are in water. Okay, and it is defined as, well, it's defined as what I just said: concentration of dissolved salts. But its units are parts per thousand, like this. It looks like a percent. Percent is parts per hundred, right? That's a 0 with a slash and another 0. Well, parts per thousand is 0 with a slash and 2 zeros. And that's PPT. If you see PPT, that's parts per thousand. You'll see it in the book, in the notebook, the workbook and the textbook and other places, other things that we do in here. It's quite an important concept for marine science, because we're studying the ocean, and it's constantly talking about salinity, because it plays multiple effects in how the behavior of water and ocean currents and organisms' behavior as well. So we're going to talk a lot about salinity. So the average is 35 parts per thousand, PPT. The highest salinity recorded is in the Dead Sea in the Middle East, with 33.7% salt, or 337 parts per thousand. So this would be 3.5% salt for regular water, okay? And then the Arctic is about 32%. We'll learn about why that is soon, okay? And this map is just showing salinity grams per kilogram, which you did a little bit of an activity on out of the workbook recently. You graphed it. You graphed the Atlantic and the Mediterranean up here, and then off the coast of Kuwait here in the Gulf of the Arabian Gulf, or whatever it's called, the Red Sea, I don't remember. Okay, so investigate the effect of salinity on the freezing point of water. Again, a very simple concept, okay? You see that as salinity increases, amount of salt goes up, the freezing point decreases or gets depressed, okay? It gets sad. The freezing point goes down. So the saltier, the more energy you have to pull to freeze water, okay? So so I've had a cup of salt water and a cup of fresh water, and I put them both in the freezer, and I came back in an hour or two, the fresh water would be frozen or starting to freeze, and the salt water would still be liquid. This is clear as well. If you put a bottle of water in the freezer and a bottle of Coca-Cola in the freezer, the water will freeze first because the Coca-Cola has dissolved solutes in it. It takes more energy to push those solutes out of the crystalline structure of the water, and so that's why it takes longer and more energy. Explain the effect of surface runoff, precipitation, and evaporation on the salinity of seawater. So how do these things run off when it rains, okay, or rivers, I should say, because the river still flows into the ocean if it's not raining, right, for quite a while. So rivers, streams, and all that stuff run off. Precipitation, that's just raining right down into the water because it's an addition of fresh water. And of course, evaporation, which is, we talked about last time, which is water leaving the surface, even though it's not boiling. It's just the particles at the surface of the water that have gained enough energy to fly out, right? So if you add water, simply put, it's going to dilute, it's going to water down, it's going to decrease the salinity. So again, runoff precipitation and melting of sea ice. So you have all this ice, the ice is fresh water, right? And when it re-enters the saltier portion below, it's going to dilute it. Also, removing salt. So sea spray, when if you've ever parked your car long enough on the side by the ocean, or if you perhaps live by the ocean, you know that you get this mild coating of, you can go like this across your windshield, and it goes like that, makes that sound, and it's salt. It's salt, like especially on windy. It's been windy for a couple of days, blowing that salt into the air, and that's why if you look at things by the sea that are metal, they typically have spots of rust on them, because the salt initiates or speeds up that process of oxidation of metals. So anyway, so salt will come out of, on windy days, out of the ocean, because the water comes out and then it lands on things and the water evaporates, leaving the salt behind, and the salt leaves, okay? And then absorption by organisms and fish. That's the lowest. These two are very small. But yes, all organisms will absorb some of the salts, dissolved solids, into their bodies. Not just fish, though, sea stars and whales and algae, okay? And then if you remove water, you're going to increase the salinity. So obviously evaporation is going to make it saltier. The reverse of melting of sea ice is obviously the freezing of sea ice. So in colder temperatures, that's going to increase the salinity. And then also by adding salts and chemicals. So here you have lava from a volcanic incident pouring into, this is probably in Hawaii, pouring into the sea, and that's going to add dissolved solutes, or solutes to be able to be dissolved in the sea, as well as hydrothermal vents. Those, they call them black smokers. I mentioned it in the last notes, that are at the bottom of the ocean, pumping out this like highly mineralized hot water from inside the earth into the ocean. And then of course something called atmospheric dissolution. Really this is just particles in the air that are dissolved in the air that touch the surface of the water, and when they do, they become dissolved in the water instead. And so again, that's the lowest possible method of reintroducing solutes into seawater. All right, slide 22. We're going to describe the pH scale as a measure of the hydrogen ion concentration in water, including the terms acidic, neutral, and alkaline. This is a review. Those of you who, again, had physical science in 8th grade or in 9th grade, you know this very well, okay? Or chemistry. So here's the pH scale in two different ways, and everything that's 6.9 and below is to 0 is going to have a higher concentration of hydrogen ions, and therefore will be an acid, okay? And see, hydrogen ions are greater than hydroxide ions, okay? And then the opposite of that is going to be where the hydrogen ions are less than the hydroxide ions, and that would be from 7.1 to 14. It's not exactly that clear, but for this class, just know that it's clear enough. And those are your bases, okay? And here are some examples. So acids are like stomach acid, gastric acid, soda, black coffee, okay? And then you've got pure water right in the middle, which is a neutral, 7. Only pure water. I don't know if anything else would register as neutral. Well, you only measure water-based things anyway this way with pH. I think that's like a unspoken kind of thing. And then bases are, seawater is slightly basic. So that's kind of important to understand for future reference. We definitely don't, if your seawater is acidic, or if you're running a fish tank, or if there's an acid spill in the sea from some industrial incident or something like that, you just know that it's going to be bad for marine life, okay? And then demonstrate the use of litmus indicator, universal indicator, and pH probes to measure the pH of water. We are going to use a virtual pH probe in this class. This week, we're going to do a lab, online lab. I have papers, and you're going to follow the instructions on the papers, and you're going to fill it. It's actually rather simple, but it's just kind of an online lab, virtual lab, where you take a pH meter and you put it in different virtual solutions, and you're measuring the pH with that pH meter. Litmus indicators are just little strips of paper that you dip in. You may have used them before, that change color. And if it's red, it's an acid. If it's blue, it's a base. Simple. And then this is just a universal indicator chart. So depending upon what color your solution changes, when you use an indicator, it's just a couple of drops of a substance that you put into your solution, and if it changes color, you just use this chart, and whatever color it matches to, that is the pH. It's rather simple. I'm not even sure why it's in this. It's too simple. Okay. You need to know that oxygen has a lower solubility in water than carbon dioxide does. We did mention this in the previous notes in part 1. But it's all by itself here. And the reason is because of polar versus nonpolar, right? Because water is polar, and therefore it dissolves polar things a lot better than it does nonpolar things. And carbon dioxide is polar. Oxygen is not. It's two oxygens. It's the same on both sides. It's nonpolar. But carbon dioxide is polar, mildly polar. So 200 times more soluble carbon dioxide in seawater than oxygen is, okay? And of course, as you increase the temperature, solubility of gases goes down. Opposite of solubility of solids. Solids goes up when you increase temperature, the whole candy thing, remember? All right, and that's what this is talking about, solubility of gases. So you need to describe the effect of water temperature, pressure, we're gonna talk about each one of these things. Pressure increases with depth, right? Atmospheric pressure, so the greater the atmosphere, what happens? Salinity on the solubility of gases in the water, and what that means for marine organisms. That's the kind of kicker here, okay? So we're going to discuss those, but what does it mean for life in the sea when that changes, and behaviors and migrations of organisms and whole pods of whales, and the daily migration of deep water organisms up to the surface at night and then back down to the deep again during the daytime. It all has to do with all of this seawater chemistry. It's rather quite fascinating. All of it combined together, and how sensitive it all is. When we overfish or when we pollute, it affects all of these systems, and it's very important to know what we do has an effect on the bigger stuff, what we do positively and negatively, right? The bigger picture. So water temperature, okay, the colder water gets, okay, the colder the ocean gets, the more gas it can dissolve, okay? So cold water will have more oxygen, and warm water will have less gases. When you heat water, the gases leave. So if I had, again, let's look at a marine example. If I had a tidal pool where the water at high tide was here, and then the tide went out and it left a pool of water and some rocks, and the organisms that were living in there, as the sun throughout the day beat down on that tidal pool, the temperature of the water would rise, not very quickly because of the high specific heat of water, but it would rise, and the oxygen would start to leave. You wouldn't see bubbles leave, but most likely, but the oxygen would exit into the atmosphere because the water temperature is climbing, and so the oxygen solubility decreases, and the fish would be like, help, until the next tide came in and provided fresh water again for them. This is much clearer when you think about a soda bottle. Haven't you ever tried to open a warm soda bottle? It usually doesn't end up very good. It usually bubbles over, right? But a cold one right out of the fridge won't do that unless you shake it up, but we're not talking about that. Just comparing warm with cold, and that's the only variable, because the increased temperature makes the carbon dioxide in the soda want to get out fast, okay? Pressure, depth. So the deeper you go, what happens? So here you have pressure, excuse me. Pressure is increasing, and here is the solubility of carbon dioxide. As the pressure increases, you can clearly see the solubility also increases, okay? So increased pressure, you're increasing, you're going down in depth. So the pressure of the water pushing down because of gravity is going to be greater, right? That's going to increase the solubility of gases. Atmospheric pressure, same thing. The atmosphere is pushing down on the surface of the sea. Here you have, temperature is not really involved in our conversation right now, but here you have oxygen solubility. I don't know why they spelled it with an E here, oxygen, I don't know. Excuse me. But you can see that pressure in millibar, in bars, blue is 1, 2 is red, and 4 is yellow. Higher pressure in yellow, the highest pressure in yellow. As the atmospheric pressure increases, the solubility increases, okay? So that's because it's pushing down more on the water, so it's going to be in more contact with the water, and more gas can enter the water, okay? And it's also going to prevent gas from escaping the surface of the water if it's more atmospheric pressure pushing down. And then, of course, increased salinity equals the decreased solubility of gases. So here you're comparing fresh water with seawater. The fresh water is the lighter color on the top, and the seawater is the darker color on the bottom. And the more salt, that's the dark blue, the lower gas content. Why? Because there's not enough room. The salt is taking up more room in between the water particles, which doesn't allow a lot of oxygen in there, or carbon dioxide, or other dissolved gases. So that's why, okay? So fresh water will be able to absorb more and dissolve more gases than salt water because of the high salinity, right? Okay, so we're almost done. We're on slide 27. Describe the effect of water temperature, pressure, again, depth, atmospheric pressure, and salinity on the solubility of gases and the implications it has for marine organisms. So we're still continuing with kind of the same subject. Again, why is there more oxygen near the surface? This is important to know. Turbulence, mixing. The wind blows over the surface, making waves. The waves churn up the surface, which really is just mixing. What is the churning of the surface of the sea, right? The same energy is like below the sea. So it's just mixing air and water. That's why you get bubbles and sea foam and those kinds of things. That's why you get white caps when the water's blowing and it turns the sea white, whenever a wave falls over, the bubbles. That's oxygen and carbon dioxide and other gases in the air mixing with the surface of the sea, okay? So turbulence increases atmospheric dissolution. More in the atmosphere than in the water. More in atmosphere than water. So it mixes the oxygen in, okay? And then, of course, photosynthetic organisms like marine algae, seaweeds, and microscopic phytoplankton that live in the sea, that are photosynthetic producers, they live at the surface. Why? Because there's light. That's where they get their energy from. They're going to live where they're getting their energy from. They're not going to live down deep where it's dark. And so what do photosynthetic producers create? Oxygen. And so that's why, 2 reasons why there's more oxygen at the surface than there is deeper down. Okay? So here we have depth. And the green is oxygen. The red is carbon dioxide. And down here we have concentration of those gases And you're going to see something very strange. The slight increase in deeper water, we'll get to that in a minute. Okay, so why does oxygen decrease beyond 200 meters? Why does oxygen make this extreme turn and decrease? Okay, so it's right there, and it just goes downhill from there. Okay, and again, that's no photosynthetic organisms, only respiring organisms. So below the light level, you only have organisms that, and we're talking about plankton as well, not just big fish, okay, are using up that oxygen in that region. And none's being made, so it has to mix. And that's why you get that decrease. And then dead organisms, decay, decomposition uses up oxygen as well. And as organisms, all organisms, from the tiny microscopic plankton to the whales, as they sink, that decomposition uses up even more oxygen as you go down further. And then, of course, this slight increase down here is because it's a lower temperature down there. And in lower temperatures, you have a higher solubility of gases. And so that's why there's this slight increase as you go down, because the water is getting colder, okay? It's also getting higher pressure. When you have a higher pressure, there's also a higher solubility, which is what we discussed on the previous slides, okay? So it's really interesting to do that. And of course, how did they figure this out? Well, you just take a sensor, not a sensor, but a little capture device that has a door on it that you can close from the surface, either mechanically or electronically, and you lower it down to the depth that you're trying to study, and then you hit the button, and it slams shut, and capturing the water at that depth. When I served on a NOAA vessel, a NOAA research scientific vessel, doing a survey out in the ocean, which I'll talk about probably many times in this class, it was called salinity temperature conductivity, STC device or something like that. And every time we did a station, we dropped this device down, and it had its little door on it and slammed shut at different depths. It's really kind of cool. So that's how they determine what the oxygen and carbon dioxide concentrations, among other things as well, salinities and other stuff, by collecting water samples from deep down in the water. You don't have to go down there to collect it. And this is just another description of that. So the red is obviously the oxygen, and the green is phosphate. That's just a different relationship, okay? But the red is the same pattern, right? And then once you pass the photic zone's way up here. Once you pass the photic zone, which is where light penetrates, it's not very deep actually. This is all dark. It's kind of creepy. That's why the ocean creeps some people out. But because when you can't see, most life is up here anyway. Most life, even sharks and stuff, are up here. Very few sharks, and this is pretty much nothing's in here usually, okay? Because oxygen's at a minimum here. So then you go back down here, and because the oxygen increases virtually back to where it was, that's why you have all these benthic organisms living down here, like anglerfish and gulper eels and weird octopus and other strange creatures that live down there in the deep abyssal part of the ocean. And we're going to talk more about these layers when we do in that future unit. Okay. All right, and then slide 29. Explain how water temperature, water pressure, and salinity affect the density of seawater again. So lower temperature equals denser water. Cold water will sink, just like cold air sinks. We mentioned this last time. And the liquid molecules are closer together, so they're denser, and they're going to sink. Just like warm and cold air. Cold air sinks and warm air rises. Increased pressure, you're going to get denser water. Because you're squeezing the particles closer together, they're going to become more dense. Remember, density is the measure of how close atoms and molecules are to each other. And then when you increase the salinity, you're just adding more stuff to the water, so you're going to increase the density. So salt water will be denser than fresh water. This is what drives the global movement of water around the planet. So if our planet is warming due to climate change and melting of ice and thermal expansion of the sea because of increased temperatures, it can disrupt those global patterns of water movement and cause severe climatic changes. So we have to be aware of this. They're studying this. There's tons of articles out there and news reports about this happening. And if you want to see a very dramatized, that's what I'm looking for, dramatic representation, portrayal of this effect, watch the movie with Dennis Quaid and Jake Gyllenhaal, or whatever that guy's name is, called The Day After Tomorrow. And it's a neat movie. Okay, so I used to show it with my Earth Space Science students when we learned about climate change. So remember, it says recall, because I'm not really teaching you how to do density in this class. You should already know how to do it. We just did some density in that activity we did earlier, I think. So it's DMV, right? I always remember Department of Motor Vehicles. I mentioned that last time. So density equals mass divided by volume. And this nice little demonstration, I put this in your notes to show you that no matter which variable you're missing, whether it's the volume or the density or the mass, you just have to move the formula around and solve for the missing piece, okay? And please know that it has to have units every single time. Here, the units are cubic meters per kilogram, okay? That should not say cubic kilograms. That's a typo. If that's in your notes, fix it right now, please. It should say cubic meters. Actually, I think the meters might be behind this picture. Oops. So cubic meters per kilogram, okay? And you could also write it this way, kilogram meters to the third power, negative third power, inverse, right? Okay, we're nearly done. State that the density of ice is lower than seawater, causing it to float. This is a huge, huge concept that needs to be made very clear, okay? So, you have to remember that everything else, when it in its solid form, will sink in its liquid form. If I took this ring, this gold ring, and I placed it on top of molten gold, liquid gold that I melted, it's not too hard to do, jewelers do it all the time, it would sink to the bottom. And if you continued to add heat, it would melt. If you let it cool down, the ring, if it didn't melt too much, would be stuck, trapped in the bottom of the block of gold, okay? So everything else sinks, is my point, except water. Because of water's unique crystalline lattice that it makes with those hydrogen bonds, it pushes out all the other solutes and leaves an empty space in between. It's called a triad, 3 water molecules coming together like this, one here, one here, and one here, and there's a space in between with nothing in it, which decreases the density, which makes it float, okay? And lots of examples on this slide. And why is that important to life? Why is that important to marine organisms? Well, I think the concept's very simple. You have organisms that live in that ice, number one, okay? And this is algae that live on the ice. If the ice was on the bottom, they wouldn't do that because there's no light, okay? Whales and seals give birth, well, the whales don't, but the seals do. The seals mate and give birth on the sea ice, and orca whales, and this is an example because polar bears hunt this way too, on top of the ice. That's where they find their food sometimes. And penguins, of course, for this example is where they're escaping the leopard seal, which is waiting to hunt them. So in the Antarctic, penguins live in the south. Penguins don't live in the north. That's another big misconception, which we'll talk about more in the future. Polar bears and penguins have never seen each other except in Coca-Cola Christmas commercials. Okay? All right. So, but if ice sunk like everything else, the oceans would freeze from the bottom up. Okay? So the ice freezes on the surface, right? And then it gets so heavy, so dense, that it sinks to the bottom, and that continues to go, and it sinks to the bottom. It's never going to unfreeze. It's going to stay frozen because it's dark and the pressure down there, and it's going to fill up the whole ocean with frozen water, and then the whole planet's dead. So if you can't see the miracle that water is and its unique behavior, how different it is from everything else, and the fact that it is different makes life exist, you have to look with better eyes than that, okay? So, and it also acts as an insulator. So when it freezes over the top, the bottom layers are insulated. That's why people are so successful at ice fishing. When they go out in the winter and they cut a hole in the ice, and they're sitting there in their little huts or without a hut, and they catch this big fish. The fish are down there living happily in the insulated water when the top is, 2 feet thick. All right, and next to last slide is something about the layers. So, okay, let me just read this for you. Describe how temperature and salinity gradients, that means you're changing through a space. It's a gradient. In water columns, and that space is called a water column. So if you measure a column of water from the surface all the way down to the bottom, that's what we're talking about, a water column. And gradient means changing over that column, over that space. So it produces ocean layers, including a surface layer, something called a thermocline, a halocline, and a pycnocline. And how subsequent mixing of these layers may occur. Okay, deep ocean meaning pressure and density. Okay, so remember, density is dependent on temperature and salinity. The colder, the denser, and the saltier, the more saline, the more salinity, the denser. And of course, dense water sinks, less dense floats. This is all just a basic concept. And so these behaviors produce these things called clines, or gradient changes in water columns, clines, okay? And you've got a thermocline. Thermo means temperature, right? A thermometer is a meter that measures temperature. So a thermocline is a gradient change of temperature. So you get a rapid decrease in temperature over depth. So here's temperature. And once you get to a certain, so it's pretty stable until you hit that end of the photic zone, and then you've got this aphotic zone, no light, which drastically decreases the temperature. And at the bottom of the sea, it's only like 2 degrees above freezing at the bottom of the ocean. It's the only reason it's not freezing is because of the pressure. A halocline, halo refers to salt, okay? Like a halogen. That's where you find chlorine and fluorine and bromine on the periodic table in the halogens. So halo refers to salt content, okay? So this is a rapid increase in salinity over depth. So salinity, you can pretty much mirror image the temperature. As one goes down, one goes up. And that again is because of pressure, okay? Obviously. And then the pycnocline is density, and which is going to mirror the salinity almost exactly, because it's colder when you get deeper, and which increases the density. And if the salinity is higher, that's going to increase the density. And then of course you have just the pressure pushing down, which is going to squish the particles closer together, which is going to increase density. So it's really all kind of simple. It's just a lot of information that takes place all at once, you know? So they're all, individually, they're all very simple concepts, but a lot of information. And this is just, this is the last slide. This is the, just another representation of temperature versus depth. This is your thermocline, okay? Thermo, and then cline. This is your column of water, and you see the gradient, okay? Like a graduated cylinder is the same form of the word because it has these graduations, gradients, okay? And this is a column, so it's a change in the, this is a change in the volume of a liquid in that gradient, okay? And so this is pretty much the same thing. This is just looking at this, the temperature, thermocline, okay? Temperature changes over that gradient. And then this one is same thing. So just you've got polar versus tropical, okay? And in the tropical regions, you're going to have, it's going to hold on to the heat a little bit more. And in polar regions, it's not going to be as much of a change because the temperature is virtually the same at the surface as it is at the bottom, only slightly warmer because of the sunlight, okay? What little sunlight there is in the Arctic polar regions. So that's our second part of the notes. Make sure you go through and you check to make sure everything's filled out. Work with your partner to double check and recheck and make sure there are no blanks or missing questions, because there are some embedded questions throughout, and then you're going to turn that in on Google Classroom. And that is all.